Wouldn't it be coming out the side of the board?
I'll draw a picture. I think it might depend on, because they don't give us a picture, so I'll draw the current on the top wire to the left and the current on the bottom wire to the, to the right and to the left. And they don't tell us the B fields. Oh, right, it's due to the wires. So using our simplified right-hand rule, what would the direction of the B field due to the bottom wire be at the location of the top wire? Into the board, into the board, into the board. So that would be the B field due to current 1. And then what would the direction of the B field due to current 2 be down here at wire 1? A couple people saying out. Anybody else? Jan thinks it's out. Anybody else want to give a stab at it? I think we all need to try this. This is our first real time where we're practicing our simplified right-hand rule. So if you're not sure, get out your simplified right-hand rule. We're talking about what is the B field due to the top wire acting down here on the bottom wire.
It's saying it's going into the board.
Okay, Jordan thinks it's into the board. A lot of people think it's out of the board. Anybody else?
It's going to be rotating, so at some point it's going in and some point it's going out.
Right here at the bottom wire.
At the bottom wire, it's going to be turning this way.
I don't know what turning this way means.
So at the top of the wire, it's going in. At the bottom of the wire, it's coming out.
You think it's different on this side and this side of this wire? We're talking about the current due, or the B field due to this wire acting on this wire.
Oh, okay. That's going into the
Okay. What about this table? I think Vin's the only one that's contributed. Do you guys know how to do this? Do you need some help? Get out your right hand. Stick it up. Put your thumb in the direction of the current I2. Jan, flip your hand.
Your thumb, I2, radius.
There you go. Curl your fingers. So above I2, the B field is coming out of the board. Below I2, the B field is going into the board. Okay. So anywhere below I2, that B2 is going to be into the board. Okay. So that's the first step. Now you use your right-hand rule. And so your current is to the right on the top wire. The B field is into the board. And so our right-hand rule says the force is up. So that would be the force of B2 on wire 1. And down here, we can all verify using our opposite that. Like that. Okay. Just want to make sure we're on the same page. This has been a test question. So if half of the points for the problem are making sure you can use your right-hand rule correctly, don't let those points go to waste. All right. So we sort of alluded to the fact that these calculations for B field would be different if you made your wire into a loop. So we're going to look at a couple situations with that. So we're going to take a loop of wire with radius A, and we want to find the B field. First, we're going to find the B field some distance x away along the central axis. Another view of that would be if this is your loop down here. You're right above the center of the wire, but you're some distance away. So this distance is x, and then your radius is a. So if you've got one loop of wire, this is all coming from that Biot-Savart law, so be happy I'm not making you derive these calculations. This would be your B field where you're given the radius of the loop and the distance away along the central axis x. If you add more loops to it, so if it's n loops of wire, then you just multiply that B field times n. So more loops just magnifies the amount of B field you have.
So, is this true for an inductor?
This is not true for an inductor because an inductor is not a flat loop of wire. An inductor is like a solenoid, and we'll get to solenoids in a little while.
So, sorry. The point is going to be from the center of the circle out. So, like, here's the circle. It would be out like that?
Yeah.
It is not up like this.
Right.
So then, how do you have more than one loop if it's not?
Just like we made last week with our motors. Kind of like this. So it's generally flat, generally a flat loop, but there's many, many loops of wire here and number of loops. That's different than a solenoid. A solenoid is a cylinder with a lot of loops like that. And in order to qualify as a solenoid, the radius of the cylinder has to be much smaller than the length of the cylinder.
Right, and then they can't overlap each other.
Right.
Okay. So then we're considering that, even though they're somewhere off to the side and somewhere on top, that's technically considered one loop.
Yeah, yeah,
Okay.
yeah. Okay, did everyone write down these equations? Okay.
Hold on, A is the, oh, radius A, it says right up there.
Yeah, radius is A. So the next slide is going to be more relevant to the experiment we're going to do in lab today. If we shrink this x value down to 0, so we're measuring at the exact center of our circle, then the equation simplifies down quite a lot. So if you've got one loop of wire, the magnetic field at the very center of it would just be mu naught I over 2a. And if you add multiple loops of wire, like we did for our motors, then you, again, just multiply it by n. So ideally, when we put our magnetic field sensor in our loop that we create for lab, it will be located at the very center of your coil. So your coil is going to be sort of like this, with these leads going off to a power supply. And so this current carrying wire will have current going around this loop. It's going to create a B field down the center of that loop, and you can create, you can do a right-hand rule on this. So if it's if the current is sort of going up and around like this, you can use your fingers to curl inside that loop to figure out the direction of the B field. And so my fingers are pointing to the left on the inside of that loop. So the B field inside that loop would be to the left. And so you're going to take your magnetic field sensor, and it's going to be positioned at the very center of that loop. And we should be able to use this fourth equation to figure out what the B field is. Okay. And in reality, it's not kind of the way I drew it would be like a constant B field at all points, but in reality, it's going to be the strongest at the very center of the loop, and then it drops off really rapidly when you get to the sides of the loop. Okay, so now we've got these four equations. We can try example 28.6. Part A should be pretty straightforward, and Part B might be a little tricky. So if you guys are getting stumped on Part B, then I can do that one on the board. So give that a stab and let me know if you're running into trouble.